Okay. So we are theoretical computer scientists looking at consciousness through a TCS lens. And okay, so this is not moving. Okay. Theoretical computer science is a branch of mathematics concerned with understanding the underlying principles of computation and complexity, especially the consequences and unexpected usefulness of resource limitations. And this comes into the informing us in model design, and also has provided new insights, concepts, and ingenious applications, for example, cryptographically secure pseudorandom sequence numbers. In this part one, I will start with an overview of the Conscious Turing Machine and give an example, and then Manuel will discuss in part two free will and the feeling of consciousness in the Conscious Turing Machine. So the Conscious Turing Machine is inspired by Alan Turing's simple yet powerful model of computation. And here we have a 23-state universal Turing machine that can compute any computable function. So in other words, what you can compute on a supercomputer or in the cloud can be computed on this machine. On the other hand, you can get your head around the universal Turing machine and prove what it can and can't do. That's much, much harder on the cloud or a supercomputer. The CTM is also influenced by Bernhard Baars' Global Workspace theory of consciousness. And Baars describes conscious awareness through a theater analogy. Consciousness is the activity of actors in a play performing on a stage of working or storage or short-term memory. The inner speech actor is often on stage, and their performance is under observation by a huge audience of unconscious processes in long-term memory that are sitting in the dark. So I'm in the stage, you're in the dark. Here's a simple, here's a simple sketch of Baars' model. And in the center, what we have is working storage. Let's see, can't get this to go. Not sure why this, okay, we have working storage in the center, that's the stage, and then down below we have many, many long-term memory processors, that's the audience, and on top we have a stage director. And on the left we have inputs coming in through sensors from the outside world to working storage, on the right we have output going to the outside world through actuators. Okay. So even though the Conscious Turing Machine is influenced by Turing, it is not a standard Turing machine because it's not the input-output map or computing power that gives the CTM the feeling of consciousness, but rather what's under its hood. And under its hood is a global workspace architecture plus what we call predictive dynamics. And these are cycles of prediction, feedback, and learning that are throughout the CTM. In addition, we specify key processors, for example, those for inner speech and model of the world that communicate in a rich multimodal inner language, which we call brainish, and plus some motivation and a minimal cognitive ability. So I want to emphasize that the CTM is not a model of the brain, nor of neural correlates of consciousness, nor of cognition. It's way too simple for that. It considers the brain at a very, very high level abstraction at levels well above that of neurons and neuronal activity. So after we define the CTM, we define consciousness in the CTM and then point out properties of consciousness in the CTM. And we derive from the model high-level explanations of phenomena generally associated with consciousness. And these include pain, pleasure, blindsight, inattentional blindness, change blindness, dreams, free will, and altered states. And those are in our papers. Here we can only mention a couple of these. So formally, the CTM is a seven-tuple, STM, LTM, input, output, uptree, downtree lengths, and coincidentally, Turing machine is defined as a seven-tuple. And let me give you a little sketch of the CTM. We start with a short-term memory, STM, and that's our stage, and it's a read-write memory, and it holds only one chunk of information. Well, this is not the 7 plus or minus 2 chunks that George Miller talks about in the 50s, but since we can get away with one chunk and we're looking for simplicity, one chunk is for us. We also have an enormous collection of long-term memory processors, LTM. These are our unconscious processors. They're parallel and they're powerful. And eventually some of these will become connected, as we will see. And this is our audience. We also have inputs and output maps, so from and to the external world. So here we have a map coming in from the external world through sensors to some long-term memory processors. And in these maps, we have a translation of the worldish language into Brainish. And Brainish, as I said, is the English inner language used by the processors in CTM to communicate with each other. It is a multimodal language used to express inner speech, inner vision, and inner sensations in words and phrases which are called gist, richer and more expressive than other languages. And this is being developed by Paul Yang, a PhD student in machine learning at Carnegie Mellon. And having an expressive inner language is an important component of the feeling of consciousness. We also have output maps that go from long-term memory processors to the outside world, and we have a translation going from Brainish to worldish, and these output maps go through actuators to affect the world. So input maps go directly to and from long-term memory processors, not through short-term memory. And this is an important component of our model, and it's also informed by neuroscience, whereas Baars has things going through short-term memory. For us, short-term memory is just a holder of a single chunk at each clock tick. We don't have a stage manager because we do not need it, and we want to keep things simple, so no stage manager. We have those functions that happen. The Uptree is the conduit for competition. And what's happening is all the long-term memory processors have information that they want to get up on stage. And they put these information into what we call chunks. And we formally define a chunk as a six-tuple. And the chunk that processor P puts in at time t has the address of the processor. So if we imagine 10 to the 7th processors, and that's sort of in accord with maybe 10 to the 7th cortical colonies in the brain, the address is just a 7-digit number. The time is t, the time it's put in, the chunk is put in. The gist is that information that the processor wants to communicate and wants to get up on stage. And it's necessarily a very compact bit of information because of the computation needs. Weight is a valence value that the processor has given to its gist. And then we have intensity and mood that starts out, as I've indicated here. As the chunk moves up the competition tree, address, time, gist, and weight will stay the same. The others will change, the other two values. So here, let's give an example of how this might work. So here I have, what I'm showing you is just two components of the chunk as it's moving up. I'm giving a little indication of the gist, and I'm also telling you what the current mood is. And the competition function that's at each competition node here in the tree, in this particular case, we're measuring f of chunk as the absolute value of mood, and we're taking the one with the highest f values to move up. So in the center here, we have pain with -5 and joy with +3. So pain wins the competition. It moves up, and its mood now is the sum of the two moods. So it's -5 + 3, which is -2. And that makes a little bit of sense. If you have pain and some joy, maybe the pain gets a little bit less. And then again, fear is going to compete with pain. Fear wins out because it's the largest absolute value of mood. But now the new fear is -7, -2 plus -5. And you might imagine, again, if we have fear and some pain, the fear might be exacerbated. So that's the particular thing here. This is a just rough back of the envelope calculation I did last night. So if we have 10 to the 7th processors, and each competition node takes maybe about 10 milliseconds, then the whole process going from the start of that competition cycle to winning takes about 240 milliseconds, which is more or less order of magnitude what's happening in the human brain. Okay. So what we do is we've actually converted from a deterministic model of a CTM to a probabilistic model for very many reasons, some of which I'll talk about. So at the each node, we put in what we call a coin flip neuron. And what that does is enables the chunk to move up with a probability proportionate to the weight of the value or the function given, the competition function given that we've chosen. So this has a very, very nice property that if F is what we call an additive competition function, then for all processors P and time T, the probability that P wins the competition that began at time T is the F value of the chunk that was put in over the sum of the F values of the chunk. And this has a nice corollary that chunks get into STM in proportion to their importance with respect to F and probability, and hence independent of the submitting processor location. And if any of you were looking at my earlier simple example and you did a little rotation, you would have noticed that depending upon where these processes are located, we might have a very, very different outcome in short-term memory. And that's not the case with probabilistic. Also, the probabilistic model has a nice property that if a processor puts in a chunk which doesn't have a huge high value, it has some probability of getting into short-term memory. These additive competition functions they're very simple functions. It's intensity plus X times the absolute value of the mood. So where X ranges from -1 and +1. And we say, and these are just the definitions, that the CTM is level-headed if X is 0, it's optimistic if X is positive, it's pessimistic if X is negative, and at the extremes, we have something we call mania or depression. And you can see how that works out. So now that when a chunk gets into short-term memory, it's immediately broadcast, maybe in 10 milliseconds, 20 milliseconds, down to all the long-term memory processors. And what's happening here is, if you might want to think about this, what we have is a mode of prediction and feedback. So when the processors are putting in chunks into the competition, that may be thought of as their prediction. And now with the broadcast, they're getting feedback. Other prediction feedback is coming when a processor puts a chunk into external output and then gets input again from the external input. That's another prediction feedback. And so built into all of our long-term processors is we have Avrim Blum's sleeping experts algorithms. And what these algorithms do is at a very high level, if a processor puts in a chunk with, let's say, a very, very high value and it gets into short-term memory, but it turns out that processor is like too bold and that chunk really, the gist is not really valuable. After a while, the sleeping experts algorithm will lower the values that that processor gives those kinds of chunks. Conversely, if we have a processor that's kind of humble or meek and it puts in a really good information, but it doesn't get into short-term memory, it'll eventually figure that out, and the sleeping experts algorithm will boost its value. And so there's a kind of balancing act coming on here. So we have this cycle of prediction, feedback, and learning happening throughout the CTM. We call this predictive dynamics. It is reminiscent a little bit of predictive processing. So let me go through the dynamics here. We have an input map coming in from the external world. Maybe there's a very scary fox out there, and the fear processor decides to react very strongly to it, and it actually gets its chunk up into short-term memory, which is immediately broadcast down to all long-term memory processors. And the inner speech or the speech processor decides to respond to that. And the fear processor realizes that the inner speech processor now has, because it's getting feedback from the external world, it realizes that the inner speech processor has answered its question, its query, and so links are formed between those two processors. In other words, the long-term memory processor A will link up to B when B answers A's call, and we use these as bidirectional links. And this is sort of the Hebbian principle that neurons that fire together wire together. But also importantly, linking enables conscious processing to become unconscious. So after a while, more and more of these links form. Many of the links form, let's say, between inner speech and fear. You might think of that as a thickening of the links. And then we have the ability to have the Poincaré effect. So after we've learned a lot of mathematics and we've thought about things, but we don't have any resolutions, we decide to take a vacation, step on the bus, and all of a sudden some of the processes pop up with this theorem that this area of mathematics is totally isomorphic to that theory of mathematics. Okay, the Poincaré effect. Okay, so now we have at least a sketch of all components of the LTM, and so we're ready to define consciousness in so we've defined all the components of the CTM, and we're now ready to define consciousness in the Conscious Turing Machine. And so we say that the chunk that happens to get into short-term memory is the conscious content of CTM at that time. And then that gets broadcast down to all long-term memory processors. And we say consciousness in the CTM is the awareness, or in other words, the reception by all long-term memory processors of the conscious content of the Conscious Turing Machine. And this constant stream of activity of chunks competing to get into short-term memory and then broadcast to the long-term memory creates a stream of consciousness. But these are just definitions. And so the reasonable of our definitions of consciousness lie in the number of concepts that the model explains easily and naturally. And as I mentioned, we look at the high level phenomena generally associated with consciousness. I'm going to look at conscious change blindness from the point of view of the Conscious Turing Machine.
Hi, Lena. Just to let you know, you've got about 4 minutes or so.
Yeah, that's all I need.
That's great.
Okay, so you've probably all seen the Whodunit video, and now we're going to look at it from the perspective of the Conscious Turing Machine. Okay, so here a detective walks into a room and he says, clearly somebody in this room murdered Lord Smythe. Each of you tell me your whereabouts. And the maid says, I was polishing the brass in the master bedroom. And the butler said, I was buttering his lordship's scones. And Lady Smythe says, I was planting my petunias in this potting shed. And the clever detective immediately says, Constable, arrest Lady Smythe. Okay. Well, for us, there's even a bigger mystery. How come we did not notice that the detective's coat has changed from a dark color to a white color? The flowers have completely changed. And in fact, the dead guy on the floor has changed his clothes and his legs up in the air, and there are a zillion other changes that have happened. So what's going on? Why didn't the CTM, at least, or us, why didn't we see the many changes? Well, detecting change in the Whodunit video would have required significant changes in the gist describing the beginning and ending scenes. And because of size limitations on conscious content, and also the clever scene transitions, caused the high-level description of the beginning and ending scenes to be essentially the same. So there's the same gist describing the beginning and end. The scene is a living room of a mansion with butler, maid, and detective, and a man laid out on the floor. Same gist. And this CTM explanation is consistent with literature on change blindness in humans, and I'll mention two of the papers that we've looked at, To See or Not to See, and change blindness and inattentional blindness by Johnson, Yao, Street, and Simons. Okay, so I'm now done with my part, but I'd like to end with the extended or embedded conscious Turing machine, maybe like Clark and Chalmers. So we can imagine also our conscious Turing machine to have access in long-term memory processors, all the most recent up-to-date technologies of the day. So we're not limiting to the processors that we put in. So with that, we have two papers. If you email us, we can get you connected with this. And Manuel will discuss the feeling of consciousness in the CTM and free will. And okay, thank you.